And I guess I will continue with Monopoly, which is a bit more complicated game than the two we have talked about previously, and why it's a bit more complicated. So first of all, we are now rolling not a single six-sided die, but we are rolling two six-sided dice. And we are adding both together. In Monopoly, there is a rule: if you're rolling doubles, you're getting another move. In our case, we'll be considering just a single player moving along the board, so the rule regarding doubles is not as important to us. So, okay, what else is kind of problematic? Well, we have 40 squares on our board. Well, this is not a big difference. We can simply, if we want to take into account 40 squares, we can simply go back to our looped problem and change our variable to 40, and this would work exactly the same. So I can actually try running it to show the point. And now we see that after 100th turn, we are not yet at the stationary probability to visit 8th square. At infinity, it's just 2.5%. If we divide the 1 by 40, we see that it's, well, multiplied by 100, so it's easier to see. So it's just 2.5. So every square is equally likely in the stationary mode. But in Monopoly, the stationary distribution will be slightly different because of the, well, in one particular instance, go to jail square, which sends us to a special in jail square. Also, some disturbance comes from the chance cards and community chest cards. And also there are complicated jail mechanics. Well, basically, and the original game ends as players go bankrupt. So to keep things a bit more simple, here on the video, I will ignore complicated jail mechanics, and also, well, I will not take into account that the game ends as players go bankrupt. I will simply assume that the game is infinite and that I care only about what are the occupations of the squares in the long term. So, okay. So still the game is pretty much solvable, and we will try doing exactly that. So yeah, I see that in the slides I haven't mentioned that there is another rule which complicates things a bit, so-called speeding rule. Basically, it's related to roll again of doubles. So if you roll 3 doubles in a row, you go to jail. We will also ignore that rule for simplicity, because, well, with this rule, without this rule, we will have 41 by 41 matrix, because we have 40 squares plus 1 special square. And if we would consider speeding, we would have 121 by 121 matrix. Similarly, if we include jail mechanics, basically that you can leave the jail by paying or by rolling doubles or on your third turn, we would also need to add additional rows and columns to our matrix. So in the end, I believe our matrix would be 1 by 23 by 123. So basically square matrix of rank 123. So off camera, I will actually solve using both speeding rule and complicated jail mechanics. So on the learning platform, you will have another file which will include my solution with both speeding rule and complicated jail mechanics. Basically, I will still not consider this one, because for this one, I believe linear algebra is not suitable. You need to consider alternative ways to try and at least approximately solve mechanics. For example, allow artificial players to play the game, basically just rolling dice and buying, for example, every property they land on, as long as they have money, for example, using like that, basically it would be a bit more, not a bit more, a lot more complicated problem if I would consider game ending. So okay, let's now move on to our script. So okay, let me close this one. Let me go back. So okay. Yeah. So yes. Okay, so let me go back. Okay, this will be a bit quicker. Just address me correctly. Okay. Somehow Matlab itself is lost, so I guess I'll have to use clicking for some reason. Oh, it did not. Okay. Doesn't seem to like me much, but okay. Okay, so let's open up. Okay, Matlab seems to be completely broken today. So let's go back to solving linear game. Wonder where my looping game solution ended up. But it should be somewhere. Okay, doesn't matter. I'll find it later on. It seems that something is very wrong with Matlab today. So okay, let me copy the code. Commenting a lot of things out for start. I do not need this one. So yeah, commenting out this one too. So first of all, as previously, we will start by building template for the role, and now our role is not 1d6, or not one six-sided die, but two six-sided die. So let me rename it 2-die role. So do no longer have n squares. Instead, I will enter 40. Let me ignore at this point the special square. And how does the 2-die roll look like? So the 2-die roll, when rolling 2 dice, there is 0 combination, which would give me a sum of 1, because on both dice I can roll at least 1. So the smallest value I can get is actually a value of 2. And there is just one way to do that. To get value of 3, there are 2 ways how to get value of 3. So basically, first die is 1, second die is 2, and the second combination is 2 and 1. So 2 ways. And basically, I could continue listing the possible combination, but basically, the vector looks like this. So, okay, I can actually manage it here. So what's happening here? So let's copy this command to the command window and look at the values. So, okay. Yes, we could do it like that. Printf %d %dn. So, okay, what I'm doing here from 1 to 12. I guess I need to do it like that. This should make, okay, what is this size of 2-die row? Somehow it doesn't like doing, and what's the size of 1 by 12 transpose? Oh, okay. I do not need this one. Still, there are some problems. Let's try doing this one. Oh. Okay, it does look. Oh, I have forgotten to. Yeah, this one was correct, and I need to do it like that. No. Is this one correct? Yeah, this one is correct. So a bit of stumbling. So what I have on the first column, I have the combination I want to roll. And on the second column, I have numbers of ways to roll it. So basically here, I can roll 1 in 0 ways. I can roll 4 in 3 ways. So it's 1, 3, 2, 2, and 3, 1. I could roll 8 in 5 different ways. So it's 2, 6, 3, 5, 4, 4, and once again 6, 2, 5, 3. So basically, it lists all the possible combinations. And what do the separate components of? I have used 0, 6 to give me numbers from 0 to 6. Then I have used 5 minus 1, 1, gave me a decreasing vector from 5 to 1. And then I have simply combined those two into a single vector. You can do that if you want. You can also add some arbitrary number, let's say pi, in the middle. Well, just you can. It doesn't mean you should in this particular problem. So, okay, so now this one should work fine. So main, yeah, it works without, oh, it does plot something. Why does it plot something? Oh, I guess I'm in a wrong directory. Yeah, now I'm in correct directory. Still. Okay, Matlab hates me today. It seems it's totally broken for some reason. Okay, let me do it like that. And what directory I am? Okay, now hopefully it will work correctly. It's my workspace. Yeah, it does contain correct values. So I can now print out 2-die roll, get these values. Oh, it's not a standard. I'll rename it a bit later on. So, but we can still examine the contents and basically adjust the same vector, but repeated 40 times over the row dimension. So size is 40 by 12. So let's now start building transition matrix. I guess I need to uncomment this. So yeah, first of all, I will be doing this one. I will be creating 41 matrix 41 by 31. Matlab here complains, but it does not matter. It complains because this value is not used later on. It's overwritten, but I will make changes to that. So now here I can rename it to die. Notice that Matlab suggests me to press Shift-Enter to rename instances of standard roll math to die roll math. I will do exactly that, and it will change the standard roll math on the line 17 and 18 of my script. So watch what happens. Change has occurred in all the places I have used that variable, which was 17 and 18 lines. So, okay, what changes do I need to make here? I need to change to 40, and this one I need to change to 80. To make it a bit more clear, I can write it as 2 times 40, because we have a looping game here. And I need to make assignment not to a transition matrix, but to a submatrix, which will contain rows and columns from 1 to 40. This way, this special row and column 41 will remain intact at this point. So, okay, I do not need this command because I have looping. So this should be fine, and I need actually, oh, okay. This one makes things a bit more problematic. Doesn't work as I wanted to think that it will work. So let me create a temporary matrix. It's not a very nice name for a variable, but I will be using it to store things temporarily. So I guess, well, I can't think off the top of my head of proper variable name at this point. So, okay, so what do I need to do with temp matrix? I need to do the folding we have talked about previously. So I need to add values in the columns 1 to 40 with the values in the columns 41 till 80. So that the loop would be actually possible. So here my temp matrix is 40 by 80. At this point it will be just 40 by 40. So I can actually now copy the temp matrix into the transition matrix. And I'll be copying it to the columns 1 to 40. So now we can also uncomment this thing. And let's try running. Oh, yeah. Doesn't sum to 1. Strange. Oh, and it's pretty much clear why it does so. Because to die roll, okay, has it clear? Yeah, it seems it cleared workspace. It shouldn't have, or probably I did that simply by automatic behavior. So our to die roll is actually not divided by the total number of combinations. So I know that we have in total 36 values. Can actually check that. So to die roll, no, not that, 36 values. So I need actually to divide this by 36. In this particular case, it does not matter if I use ordinary division or scalar division operator, because on the right hand side I have scalar number, but just this one is a bit more proper in this case, so I'll use this one. So let's run the script again and check if the test passes. Okay, it still does not sum to 1. Why? Oh, okay, I know why. But let's actually inspect that. So you already see that 31st column is actually actually 0. So this will not actually work, this test, until we define some kind of what happens with the jail. So in this particular case, let's just, before adding anything complex, let's consider that anything that ends up in jail stays there. So let's now try running the test main. And the test now passes, and we can look at transition matrix. So the transition matrix looks like that. So basically, we have one probability, one transition more likely than the others, and that corresponds to a roll of 7, because 7 is most likely value, rolling to 6-sided dice, and we see that the looping actually occurs around, well, from the square 34. When you add 7, you get 41, and when you loop, you get that you can visit value 1. And here we have very yellow square, because, well, here we have probability of staying in jail being 100%. So, okay. So we need actually now to remove this line, because first of all, we will be dealing with go to jail square. If we go back to the slides, we see that that square is number 31. So how do we deal with that? So all particles moving into go to jail square need to end up at the jail, special jail cell. So what will happen? So here we are doing the so-called, well, I guess the most proper word is rerouting. So basically we have particles, here are the probabilities, to visit square 31 from any other square, and we're moving instead instantaneously to the special jail cell, to 41. So for this to actually work, we need to set these values to 0, because particles no longer stay in the go to jail cell. Instead, they are instantaneously sent to a special in jail cell. Similarly, we can't leave go to jail square, because we are never staying at that square. So I guess this one can be present. You can also delete it. Nothing will change, I guess, but for sake of clarity, because I'm not intending to allow any particle to stay in go to jail square, I'm also not intending to allow any particle to leave that square. So, okay, what we need actually to deal with now, we need to figure out a way how the particles can leave the jail. And I'll assume that, for example, people pay a fine and are able to leave the in jail cell special square instantaneously. So we need here to actually change this value to 11. Why 11? Because, well, just visiting an in jail square, they correspond to the same thing. They're effectively the same square, because when you roll 1, and let's say you roll 2 from the just visiting square, you're getting to the utility, to the electricity square, number 13. Also, the same happens if you roll, let's say, 2 on the from the in jail cell. You can also move to the same number 13. So actually leaving this special in jail square is exactly the same as leaving just visiting square. So let's actually mirror that by entering number 11 here. So this should deal with go to jail square. And okay, we will still need this code at some later point. And we will not be needing any of these. So let's try running that. Okay, now the test is not passed because, well, we are not leaving cell square 31. And to make an exception, we can write a bit more complicated test condition. And that test condition would be that either sum is equal to 1 or it is equal to 0. So we'll copy this one. And instead of subtracting 1, we will be just checking if absolute value of, okay, yeah, this one, not this one. So I guess I have deleted too much things because we want this in the parentheses. So, okay, let's keep it like that. So yeah, let's do 0, 0 or 1. So I have updated error message. So let's now test, and it passes fine. So let's look at the transition matrix. And yeah, what we see here, go to jail cell is removed from the destinations. Instead, every particle which visits 33rd square is instantaneously transported to the special jail cell number 41. Also, when you're leaving square number 41, special jail square, you're leaving exactly the same as you're leaving square 11. So things match up quite nicely. And I guess, yeah, let's add get stationary distribution. Okay, it's not values, it's vectors first and values next. Okay, now this should, yeah, I need to square this. Let's look at the thing. Okay, Matlab still hates me. Okay, it's not any values, it's eigenvectors. Okay, basically we no longer see the flat surface, we instead see that there is some kind of strange thing going on around, I believe, yeah, cell 18. So why does cell 18 peak over all other values? It's because, well, you're more than likely end up in jail. And then when going from jail, if you roll 7, you end up in the 18th square. So it's most likely square to be visited. If we are actually, let's combine 11, square 11 together with square 41. So we actually have only 40 squares. Okay. Yes, yeah. This will remove special square from our stationary distribution. Instead, it will put all the particles into square 11. So let's run the script now, and we see that actually a lot of particles end up on the square 11, which contains both just visiting and our special GL square. Then the next most visited value is the 18th value. What we actually now need to deal with is actually, okay, so I'll be editing code here. So yeah, so here we need to actually think about how do we deal with community chest cards and chance cards to finalize our solution. So let me start with community chest, because community chest is the simplest, and from that we can derive our further exploration with chance cards. So okay, yeah, dealing with community chess cards. So community squares are squares number 3, 18, and 44. 3, 18, 44 for square. I'm using for cycle because I know that I'll need to deal only with this many, only with these listed squares. So what I need to do now, what are the possibilities of when you hit the community chess cards square? You are drawing basically one of the 16 cards. And let us assume that as soon as you draw a card, you shuffle it back into the community chess deck. So it would be, well, using both linear algebra and a bit more advanced solutions, it would be pretty hard to track which cards were drawn and which were not drawn, and it would increase complexity both of the code and the transition matrix considerably. So I'll be considering drawing the card and then shuffling it back into the deck. So okay, so what can happen? One thing can happen, we can, well, go to go, or go to jail. Actually, keep it, or stay. So how does going to go happen? So it happens exactly, not exactly the same, but similarly to this thing here. So yeah, so transition matrix to the go square will be, transition to that square will be more frequent because of the transition to the current community square. It will not be 100% of transfer because there is 1 of 16 chance to draw that card, because it's just one card of the 16 cards. So okay, this deals with going to go. So going to jail is similar, 41 instead of 1. And then there is a probability to stay. Probability to stay is just, it's not a sum. There is 14 and 16 chance to stay. So basically this decreases the probability that you will actually stay in that square. And this increases the probability at the expense of the transition matrix. So this deals with community chess cards. And now we have to deal with chance cards, which will be a bit more writing, but from the programming perspective, it's not much harder. We'll just have, well, there will be some changes because chance cards are a bit more complicated in the rules. So, okay. Squares of chance are 8, 23, and 37. 8, 23, and 37. Okay, now let me move this. Oh, I'll later explain why we need to move, and I'll move that at the point. So we can go both to go and jail from the chance card, so it's fine. We can also visit 6, 12, 2 and 40 squares by drawing a card. So, okay, go to St. Charles place, which is, sorry, 12. So here we just, okay, I guess I can write a 4 cycle here to improve a bit more. So let me refactor my previous code. Destination squares will be 1 and 41 for destination squares. So I guess I sacrifice a bit of clarity of the code to make it a bit more, well, easier to program. You can actually add the comments, go to go or jail. So there are just 2 destination squares, each equally likely. So here I will also have destination squares and 6th, 12th, 22nd, and 40th. Also, there are a few special squares. So there are 4 special squares. 2 of them are, well, not squares, orders. There are 4 special orders, and 2 of them are identical. So let me encode them as -1, -2, -2, and -3. So in this way, I take into account that there are 2 -2 orders. And okay, let me copy the for loop. Reading St. Charles, Illinois, boardwalk, jail, nearest utility, nearest railroad twice, and back 3 spaces. Okay. Okay, I guess I can delete this one. I can delete this one too. And I am staying in 6 times of 16 because there are 10 orders to do something, 10 cards ordering you to do something. And I have to do this one only if my destination is positive. I will be doing this one. Else. Okay, and else is, I guess, easiest to deal with, or I can do it in a bit smarter way. Let me try doing that. Let me keep this formula exactly the same. We define true destination is 0. So by default, true destination will be destination. Well, let me rename it for brevity as true dest. And then, okay, I'm introducing a new variable because those special cards will change the true destination. It will not be -1, -2, or -3. It will be something else instead. So if dest is -3, let's say it's back 3 spaces, it's easiest for me to deal with. In this case, dest is simply -3. And notice one thing, that 37 -3 is 34. And I will have to deal with community chess cards after the chance card. So this is the reason why I need to move this code in front of chance cards. So I believe this is the only case when you have to deal with with this monopoly specialties in the particular order. So I guess this is a quick hack, a quick fix to this. So, okay, now I need to deal with other special orders. Well, I can add comment back 3 spaces. So let's deal with -2, nearest railroad. So how to deal with nearest railroad? Railroads are in positions 6, 16, 26, and 36. And when you're going to the nearest railroad, you're advancing, so you're going forward. So what can I do about that? Can I do it in a smart way, or do I need to use if statements? So let's say if well, it's likely possible with modular arithmetic, but let's do it in a simpler way. So if destination, so now this, oh, not the destination. I need chance. I need my if statement to depend on my chance square. So if my chance square is after the first railroad, but before the second railroad, my true destination is the second railroad. Similarly, if my chance square is after the second but before the third, then I need to move to the third, and finally, well, not finally, because we have to deal with the first railroad too. This will be simply else. So this should cover all the cases. I could write written simple code just for specifically for 8th chance square, for 23rd chance square, and for 37 chance square. I'm just writing it in a bit more general way. So it's fine. And yeah, our minus first order is nearest utility. So we move to the nearest utility in exactly the same way. So I'm just copying. Nearest utility. But now my utilities are 13 and 29. So okay, logic is exactly the same. Okay. So if I have already passed the electricity, but not yet passed waterworks, I go to waterworks. Otherwise, I go to electricity. So this should take care of everything. So let's try running the thing. Okay, there is some error. Line 58. Which is line 58? Okay. It's not valid through list. Oh, -6. Why it's -6? Okay. Well, I guess we need to go into the debugger mode. Okay, I guess I'll have to expand this one. Okay. Now the value of my true dest is 0. So I guess it's more or less safe to press continue. If I press tab, it simply goes to the next command. If I press continue, it will loop until it goes to the next breakpoint, which is line 38. So let me go. And it has looped. Now my true dest Oh, okay. I guess I need breakpoint at line 39 instead, because when I break at line 38, it hasn't yet run line 38. So continue. Okay. It's 6, so everything should go fine. Now it's 12. Let's continue. 22, everything is fine. 40, everything seems to be fine. -1. Okay, let's check if -1 works. Yeah, it seems to work. Does -2 work? Does seem to work. Does -2 another? Oh, -3. Does seem to work. And yeah, with -3. Oh, okay, yeah, this is the error. So -3 and -3 is actually -6. So here we need not dest, but we need SQ, because SQ is our current position, and we need to move 3 squares back from our current position. So I guess I can hide these so they do not distract us. So let me clear everything. Let's run. So everything has run, and the stationary distribution we get looks like that. You can also plot the transition matrix just for the sake of curiosity. So, okay, it looks quite more complicated than initially because of the chance cards. So chance card 1 occurs at 7. Oh, sorry, at 8. Another occurs at, well, another special thing occurs at 18. Oh, 16. Oh, okay, I guess this is increased because of the jail tile. So yeah, from 22 you can move somewhere else. Or have I mistyped? No, it's 18, it's fine. So we can actually examine it a bit more closer. So I care about the departures from the 18th. As you see, I can visit Go Square with small probability, and I can also visit Boardwalk Square also with some small probability. So I guess this is fine. This is correct. So the distortions basically we see here are occurring because of community chess cards, go to jail square, chance card moving particles to moving our players to our squares, and basically those players starting from that square their next moves. So I guess this is the reasons for most of the distortions. So okay, so we can look at this one. I guess a bit more proper way would be to do bar chart. Let's rerun the script. Oh, okay, we'll complain about this one. And we can actually make that plot a bit nicer. So I guess this is a bit, this is actually our end result. And actually we can now start to reason about which squares are more profitable. But given that we're going a lot over time, I will not do that. I also do not know nor the costs nor the rents for specific properties. But I guess the point is that the second most visited well, we can actually take a look at side by side, can produce still a quite reasonable an interesting result without actually resorting to the actual calculating rents and prices of a property. So let's calculate probability to visit certain to visit a property of certain color. So brown will be stationary. Brown stationary dist 2 and 4. Some now prob cyan is 7, 9, and 10. Prob magenta 12, 14, and 15. Finally, prob orange 17, 19, 20. Prob red 22, 24, 25. Prob yellow 7, 28, 30. Green 2, 33, and 35. Finally, prob blue 38 and 40. Okay. Print F. It's a brown. Okay, your line symbol. Yes, yeah. 8 properties. So, okay, cyan, magenta, and I still need to make changes to the text. Okay, good. So let's run the script and see what happens. Okay, I haven't multiplied by 100. Get the percentages. This is actually why it's better to use 4 cycles and to put this thing, let's say, into salary. Basically then loop over the elements of a salary. But I'm doing that so that it would be as quick as possible. So now after running, we actually see the probabilities. And well, the probability to visit brown is small. It's kind of expected because there are just 2 properties in brown. Similarly, probability to visit blue is also quite small. Actually, let's, as far as I know from other solutions, probability to visit park square, which is the first property of the blue ones, should be quite small. Yeah, it's just 2%. Oh no, it's boardwalk around 2%, 2.6, and a probability to visit Park Place is just 1.8%, and we can actually later on make some rankings. Let's now just look through the probabilities to visit properties of various colors. So the biggest probability is to visit actually red properties. With quite close by, we have probability to visit orange properties. So basically, if you're playing Monopoly, it's best if you actually get those red properties first. But well, it depends. Orange is quite good too. Basically, well, if we would calculate properties, they will both rent prices and card prices, property prices, blue would not overtake the orange and red. So, okay, so we can actually now try produce a ranking of properties. So ranking. So I have probabilities. I guess I need to look up the documentation of sort function. Or does this thing exist? No, it does not exist. Okay, yeah, I'm interested in this one, and yeah. Okay, so I can use sort function to get the ranking. I do not care about the first output keys. So yeah, I want to sort stationary distribution, and I want to sort it into this descending order. So for idx in keys, print f. So yeah, 0 to 10. Now let's avoid zeros. And let's do it like that. Not 2, let's say 4 to f. 10%. Let's add a few spaces. New line symbol. So idx, stationary dist. This should do the thing. So this should give us the ranking along the probabilities of the properties. So I can run just this section to avoid. Okay, there is some error. Okay. Oh, it's not permitted to ignore a value. Oh, yeah. I need to do it like that. Basically, you can use tilde character. For example, in this case, I do not need actually sorted values. I care only about sorted indexes. Sorted indices. Like that. I do not care about actually sorted values. I need only the indices. So I tell Matlab exactly that by using tilde. So okay, now I should be able to run just this section. Okay. What happens if I do it like that? Will it be a bit better? Okay. Matlab does not like me very much today. Okay, it's strange. Yeah, it should be fine because, well, the numbers here are fine. So what is actually happening here? Well, let's just do this x. Well, this is alternative to using debugger. And yeah, everything seems fine. So sorted indices. are fine. So what happens if stationary list of, let's say, 3? Yeah, it's fine. It should be printed nicely. Yeah. Okay. Yeah. Okay, let's go back to 2D. Well, let's try running whole script. Why does Matlab do that? Okay, what if I try to... Okay. What if I try to print out just IDX? Maybe D is not proper. Let's run. Yeah, and now it prints out nicely. So why doesn't... Let's skip this one. And yes, couldn't do it like that. Yeah, 2F print F. Slightly cheating. Okay. Let's try what happens now. Okay, it seems that sorted indices. What's the shape of sorted indices? It's 40 by 1. I guess it doesn't know how to treat 40 by 1. Let's see what happens if I do it like that. Okay, yeah, now it... I guess it didn't like the fact that the sorted indices here in this case was a column vector. It wanted to get a row vector. Instead, M transposition has fixed this. So yeah, I guess I can go back to the original a bit more proper way to print things out. It's okay. Yeah, let me close this one, open up the command window. I have just cleared the window. I haven't cleared the workspace, so I can rerun this section just to get the ranking. And we see, well, least lucky list visited squares are number 8 and 37, which corresponds, number 8 is, well, this chance, which is very logical because in the 10 cases of 16, you are leaving this square. Similarly, 37 is also a chance square. You're also leaving it quite fast. 23 is, I guess, another chance. Yes, 3 chances at the bottom. The last one is go to jail. Now the next few visited are 2, 3, and 4. So 2, well, 3 is a community chest. 2 and 4 are brown properties, so it's not very good investment. 2 and 4, but the 39 is taxation, superior income tax. And well, now we have Park Place, which is 38. So basically, yeah, it's one of the least valuable properties among those on which you can build. Only 2 and 4, only 2 Brownian properties are less visited than the Park Place. So it's pretty terrible investment. So I guess the best values are basically in this corner, simply because of the fact that jail is here. So there are multiple ways how to hit orange and red properties, and the particles are constantly being resetted to the jail square. So I guess this is it for solving monopoly. So my code, the one I have written during this live session, will be available on the e-learning platform. Slides also, video also, and also I hope to add my code which solves a bit more complicated monopoly problem, in which I actually try to include doubles, speeding rule, and actually complicated way of leaving the jail, basically not paying the fine as soon as you get to jail, but being able to leave the jail by rolling doubles or on your third turn. So that solution is it's not a lot more complicated, it just it takes a lot more time to code that thing. And we are already running quite over the time I have planned to assign to this lecture.